Hello and welcome to my first non-journal uh, video in this maths thing which I'm doing. Uh, I've noticed that in my journals I just write down as much as I can, and that's probably not conducive to a good viewing experience, so I've decided to try and write more drawings because I'm just going to explain over everything anyway, so I might as well. And things which I might as well do, I might as well start. So, uh, this is a video on category theory, so the first obvious question is, why bother? And the first is, sim in terms of the actual structures, basically, it's not very difficult. So a category is a sort of directed graph where you can imagine going along paths, and uh, the basic objects of proof in category theory are commutative diagrams. So diagrams like this. So you see these paths, this is meant to represent the same as these paths. And these dotted arrows, this is a definition. So this is defined such that it has these two paths, and for any other object with these two arrows, there is a unique arrow this way, such that this so-called commutes. So a diagram commutes if any path connecting any pair of objects is essentially the same. So this diagram is meant to commute, for instance. So in reality, uh, this diagram is defined with a third one. So this commutes with these, but I mean, it's really not necessary to include this because if these commute anyway, then this automatically does. And I think it's probably a good idea to think about why. However, I said it unifies these definitions. This definition is a product. So within the category whose dots represent sets and whose arrows represent functions, this represents the Cartesian product. In the category whose objects represent modules over a ring and whose arrows represent module homomorphisms, this is the, well, the direct product of two modules. However, if you have seen my journal entries, then it's the same as the direct sum, and that's a special fact about the category of R modules, which I have yet to prove. However, uh, I think it's best we move on to the next one, otherwise we will be here all day. The next reason is more of an added benefit, is that it condenses a tremendous amount of information into pictures. So I will show on the next slide, there is a definition which takes up maybe 5 or 6 lines, and the picture is 7 things, and you just say this commutes. uh, and it's already kind of used a lot, and categorical definitions and things are used a lot within algebra, differential geometry, topology, representation theory. There's more and more and more, but those four are the things which I've written down and written down notes for. So in algebra, Hom and tensor, those represent two functors. Kernel and co-kernel are two limits within category theory, which I will describe probably in number 3 if I continue this. And the exact sequences I've talked about in my journal, that is a categorical object within the category of complexes over a particular abelian category, which is a particular type of category. Within differential geometry, you have sheaves and stacks and tensors again. So a sheaf is a particular type of contravariant functor from a particular category into wherever. A stack is a sheaf whose uh, category, whose objects you're defining into is the category of categories, which might seem like it's a issue. It's definitely not. Uh, we will talk about this at the end. Within topology, you have spaces over a particular topological space that represents objects within what's called an overcategory, which whose name comes from exactly what you'd imagine. Sorry, I'm just about to take a sip of coffee. You have homotopy and homology. Homotopy represents a particular uh, represents what's called a two-cell, which I'm not going to describe because I have not actually studied higher category theory. Homology. So in the 19th century, in the late 19th century, there were a bunch of different things which people realized were homology, but weren't actually unified into one definition. So category theory unifies definitions. These definitions were unified in the 1950s, MacLean tells us, by Grothendieck et al. Into a single theory under category theory. So that's what the definition of an abelian category was designed to do. And I've finally written representation theory, which is really an algebra topic, but a lot of diff representation theory is a really active field of study, so it it basically has as many people working on it as the rest of algebra, so it it makes sense to give it its own subject here. A representation is just a functor. Uh, if you work out if you work out the definition of a representation and look at it from a functor perspective, the study of representations is the what something is perspective on functors. So specifically a functor from some group, which is a one object category with a bunch of morphisms representing the group actions. This maybe would be C4 or V, and functors from that category into the category of vector spaces, modules, sets if you really want. But typically, how representation theory is usually taught, it's the vector spaces over C. So representation theory is just a special example of functor theory. Indeed, set theory is a special example of category theory. So, as I've discussed everything, let's move on. So, this is the motivating example for why I can justify that category theory condenses information. This is what a sheaf is, and then this is also what a sheaf is. This is 7 things and a bunch of arrows. Well, let this be an open cover. F is a sheaf if it is a contravariant functor from open X into sets or wherever you want. Cat, top, uh, sheaves of abelian groups are usually studied. Sheaves of R modules over some ring. More generally, those are very useful examples because they are abelian categories, and so you can define homology there, and the, well, cohomology in terms of sheaves. But do you see this is a much, much more condensed definition than what something is, as opposed to what it does? Uh, I've read an article by Tom Leinster called Sheaves Do Not Belong to Algebraic Geometry, where he argues that sheaves basically come naturally as the restriction of an adjunction from the I'm sorry. let's uh, let's continue. But the that is the name of that article. I think it's a very, very cool article. So sheaves do not belong to algebraic geometry by Tom Leinster. That gives you a hint as to like, well, that's a maybe 2-page article, and it gives you an introductory look at how category theorists think. This is a provocative title. Sheaves do also belong to algebraic geometry. It's a shared thing. But sheaves come naturally from category theory, and I think he uses two fairly elementary facts to talk about sheaves, where I will leave it at that. So next we go through the definition of a category from MacAlane's book, which I will discuss when we have the references up. So first he talks about directed graphs. So directed graphs, initially, you can think of as a bunch of dots and arrows, but MacLane gives a better definition. So what if there's too many dots or too many arrows and your page can't fit everything? Well, a directed graph in reality is a set of arrows, a set of objects, and two functions, one which identifies where an arrow comes from and one which identifies where an arrow goes to, the so-called domain and codomain. So for this arrow, the domain is this, the codomain is this, for instance, and vice versa for this arrow. Now, within the directed graphs, you can look at arrows where you can kind of follow them along. You can follow them along in a path. These are called composable arrows, and the path which they draw out is their composition. So the set of composable arrows is all pairs of arrows such that the domain of the second one is the codomain of the first. Now, a category is a directed graph where each object has its own self arrow. So you have some object, you have this self arrow, such that composition doesn't see it. This is what this is. And you can trace along any path. This is what this is. Such that these path tracings, if you have 3 of them, well, you're collapsing down pairs of arrows into one. So this collapsing should probably work for more than just pairs. So for any triple or quadruple, etc., etc., going along multiple in a row is the same as just taking them and collapsing them pairwise. So this is called associativity. This is called identity. I called these identifying arrows. They're not really. They're called the identity arrows, but because they represent the identity of the composition function, but it doesn't really matter. Sorry. So we should probably give a couple of examples of categories. So first is the category of sets. This is the prototypical example of, well, a couple of things. First, it's the example of why category theory generalizes set theory, but also why you need to sort of step beyond set theory because, well, if we go back to here, this is not a set, this is not a set, as we will discuss in a moment. So this is a very important category. So this, basically all of these, they have what is called a forgetful functor, which means that each of these is basically just, you can pull it back to the category of sets. You can't always, yeah, you can't always, but it, you, you realistically can. for most things. So next, for any partially ordered set, so for any set upon which you can say that one element is less than or equal to another, you can define the elements of the set as objects in a category, and the arrows representing, well, less than or equal to. So the equal to represents the identity, composition represents the transitivity of your less than or equal to, and the associativity, I mean, there's at most one arrow, so you'd better hope that the composition is associative, because if it isn't, then you've done something very wrong. This is, in fact, the very first example of what you could call a thin category. So a thin category is a category in which the number of arrows between any two objects is at most one. Now, the category of abelian groups and abelian group homomorphisms. Well, an abelian group is just a set with two different things. So you have a particular thing, a particular functor. I've not written this down in this slide that will probably come next time. You have a forgetful functor from ab to sets such that ab, you forget the abelian group structure and you only give the underlying set. Same with top. I've already said this, but a topological space consists of a set and a topology. Well, the functor just spits out this set within sets. Same with left modules, complexes. The sheaves of abelian groups and the covariant functors, these two I've not yet described. Well, the sheaves I have, just change this with ab. But it should probably be surprising that this data represents an object within a category, but it it should also not really be surprising. Well, what is something in how useful is something in maths unless you can do things with it, and anything which you do in a associative way, well, then you can really define a category because you can just pretend that you have the do nothing thing. That's what's called a free category over a graph. So a free category over this graph is just adding in the identity things here and then adding in all the different paths. So this representing this is this is this it doesn't matter, yes, and then this, and then there's another one for this and then this, etc., etc. So for any directed graph, you can construct a category from it by just considering all the paths and just adding all the do-nothing elements. But yeah, it should be surprising that these two are categories, but also not surprising because what is a thing in maths unless you can relate it to other things? And that relation is kind of useless unless it's an associative relation. Now, let us discuss the elephant in the room with regards to the category of sets. You cannot have a set of all sets. This is a proof that you cannot have a set of all sets. This is the first chapter of Bosso discusses, oh god, we have a set of all sets. Now, MacLean calls the set of all sets, or the set of all abelian groups, etc., the so-called large sets, and what we would consider sets are small sets. This is, I believe he's using the universes thing. So an element in a universe is called a small set. Uh, so Bosso gives these two options uh, for how we deal with this set theory concern. So universes, every set is within some universe, and you can relate universes, and universes have a certain set of rules. I think this is how Grothendieck. So there's something called a Grothendieck universe. Grothendieck's universe axioms are, I think, within Bosso's book, within a different. They are the same thing. One implies the other, and the other implies one. Uh, I quite like Bosso's other option, which is classes, where we give ZF set theory. So this is Zermelo-Fraenkel, I think, Zermelo, with the axiom of choice, and we extend it by adding something called a class. Now, a class, we can relate classes by set. Uh, what are they called? Formulae, I think. Formulae can define classes, but they can only have arguments within them that relate to sets. Uh, is the how you relate classes and sets. But think about classes as something larger than sets, where these sorts of paradoxes, which were talked about in the late 19th century, don't apply. But I don't aim to worry about size, so if you want to worry about size, look up uh, NGB set theory, which is the same as ZFC set theory, which is the usual one which people talk about with the addition of classes. Or you can discuss universes, which I think it's probably best to discuss Grothendieck or Grothendieck universes. This is just for if you're interested. But yes, worrying about size is not really my aim. So I think that's a good place to finish and discuss references. So this is where I got the definition of category from. This is where I got the image of sheaths from, and this is where I got the discussion of set theory from. I think it's probably best to give every single thing. Uh, the other bits, so the definition of a sheath, I think I got that from Ravi Vakil's Foundations of Algebraic Geometry originally, but it was just in my head. I know what a sheath is. Sheath, not sheath. I would probably like to discuss sheaves at some point, and this, again, I think I got from Ravi Vakil, but it's in all of those books. These are very basic tools in category theory. I think probably chapter 5 of category theory, categories for the working mathematician is probably the best place to look for that thing. However, this is the end, and as last time, I have had my I have commissioned my wonderful fiance to draw us a picture. So, thank you. Goodbye.